Away.
Thank you, and thanks to the organizers for inviting me to give a talk with home advantage. So I'm going to start by thanking the people that I did this work together with. So this is Nicolas. You already saw him yesterday, a grad student here. Eric Wieschaus. This is a project that has a lot to do with Drosophila, so we're very glad to have him on board, and Boris, of course. All right, so what we're interested in very broadly, and we already heard this in the first two talks this morning, so this fits right in, is the development of an organism from a single cell to the adult. And so obviously there are a lot of steps in between, and to me this is really sort of the most miraculous thing in nature that we can observe in sort of daily around us in all the crazy shapes and forms that nature produces. And so biologists have spent the last 100 years basically investigating the genetic patterns that pattern a body plan. But of course, just having some blueprint is not enough to build something. So you also need to actually do the building, do the motion. And for that, you need forces. And so cells generate these forces with molecular motors and adhesion proteins, so myosin and ecadherin and structural proteins like actin, microtubules. But of course, these forces are not just feed-forward readout of the genes, but there are plenty of feedback loops. And so that's really what I'm interested in, is how are these forces that are generated on the cell scale controlled by feedback loops to give some tissue scale or organ scale shape that is well defined. And development is very robust doing that, so that's a really interesting question. So I'm going to focus on a seemingly sort of very simple and almost boring process, and that is axis elongation. And it's basically the first thing that sort of the first morphogenetic event, major morphogenetic event that happens in human development, where you have the so-called primitive streak that forms, which defines the body axis from head to tail. It's the same in a chicken, for instance. And I think in Matthias Serra's talk, we'll see a little bit more of that. I'm going to focus on this process in the Drosophila embryo, where the geometry is a little bit different. So here it's a disc. Here it's this curved ellipsoidal surface. And we see actually this so-called convergent extension process, or shear flow to physicists, twice on this. So down here is the actual germ band, which elongates and sort of wraps around the pole and narrows along the perpendicular axis. And then there's also this tissue up here, which undergoes the same process, but sort of in the opposite direction, because this is a closed surface, so these things have to cancel out in total. All right, so as I already said on the first slide, the questions now are, where do the forces originate that drive these motions, right? This is not obvious from watching movies like this, where the forces actually originate. And then once we know where they originate, we can ask how are they coordinated on the cell scale. And sort of something that's maybe not so obvious from this is the question of how can we reconcile fluid-like behavior. So this sort of to the eye looks like a fluid flow, so we could think, oh, this is a fluid, but then tissue also resists external forces, so it behaves like a solid. So the question is, how can these things be reconciled? And I guess my title, Active Plastic Flow, is already sort of a hint at how we think that works. All right, so let's get back to sort of the fluid dynamics perspective and treat this motion here as a fluid flow. So we can do PIV, we can measure the velocity field, and we can ask, well, what would be a model that reproduces this velocity field? And here I should say there's not really friction. So the only dissipative force that we have here is viscosity. So this is on the left-hand side. And then there's some driving force on the right-hand side. And the driving force here comes from myosin. So there are myosin motors that exert active stresses. And so the divergence of that stress gives us a force that's driving this flow. And here we are seeing sort of a flat, unwrapped projection of the embryo with in red, the dorsal ventral, so back to belly axis that we see here. So this is the bottom of the embryo, this is the back of the embryo, and then the head to tail axis is here. So if we've unwrapped the surface, this is microscopy image of myosin, and we see that there's this myosin gradient from the back to the bottom. And so that generates a force, a net force, which drives this flow. And then because this is this ellipsoidal surface, the flow sort of wraps around over the pole at the tail. All right, so it turns out that we can actually make this quantitative, or rather Sebastian, together with Boris and so on, did this in 2018. They measured the myosin from the microscopy. They transformed it into a tensor, so you do some radon transform and you build a tensor out of your microscopy images, a tensor field. You plug it into this equation, and it gives you to 90% accuracy the observed flow. So we know really that the myosin is driving the flow, and you can test this in genetic mutants where the myosin is modified, and then accordingly the flow is modified. But what this doesn't answer is how the myosin is actually controlled, right? So now we know where the force originates. It originates in the myosin, in this myosin distribution, but we don't know how it's controlled. We can't predict in the future. So we could say, well, maybe it's just a feed forward from genetic patterns, and one can test this. And without going into the details, I can just tell you it fails. I'm happy to talk more about this offline. For basically fundamental reasons, this doesn't work. You can't use a fixed readout of genetic patterns. Okay, so that's the question, right? And you already know that doesn't work. So then, just sort of as a short teaser, Vincenzo is still here, I guess. So that's the part that he didn't get to talk about yesterday. So one approach to try to solve this problem is sort of to take the microscopy images of myosin and ecatirin and other sort of cytoskeletal proteins and do a machine learning approach, sort of top-down machine learning, and then come up with an interpretation at the end, come up with equations and an interpretation. That's not what I'm going to do. I'm going to do the opposite. I'm going to start from the bottom, from observations just of the cells, and this is the movie that you already saw earlier, of the cell outlines. So this is an epithelium, so all the cells are confluent. We already had 2 talks on this, so I'm not going to repeat all of that. And we see now here the cells color-coded sort of along the dorsal ventral axis, just for you to follow this visually. Then there are some sort of light gray cells that pop up here. These are cell divisions. We're going to ignore these. Over here is the head, which we're also going to ignore. But you can already see from these colors that this process on the cell scale is very tidy. It's very coordinated. There's not a lot of mixing going on. And we can also zoom in a little bit. We can distinguish the different processes that now contribute to this apparent tissue flow. So these are cell shape changes, which we see, for instance, here on the dorsal pole, right? So there, these cells get stretched as the tissue flows. And there are many cell rearrangements, which we already have heard about a lot. And just to sort of emphasize the point how organized these are, if you look at these sort of striped, artificially colored cells here, then they basically very tidily sort of intercalate with their neighbors. So the question is, how do the cells do this? So the forces that drive this are generated at the junctions between the cells through myosin motors. And if you do a laser ablation, so if you cut one of these junctions, you see a very rapid recoil, so within sort of less than a minute here. And that's much faster than the timescale on which the tissue flow itself happens. So there's a timescale separation, and on the fast timescale, force balance is established, but on the slow timescale of morphogenesis, the tissue is basically in quasi-static force balance. And what we can do then is we can take the observed geometry, meaning the angles at which these junctions meet in vertices, and we can solve the force balance equation for the tensions that exert these forces as a function of the angle. So we can infer the forces. And visually, you can see this down here. So if opposite of a junction you have an angle that is larger than 120 degrees, then that junction is under lower tension than its neighbors. If the angle is 120 degrees, you're in a situation like in a foam, where all the tensions are equal. And if the tension is higher on this inner junction, then this angle is smaller than 120 degrees. All right. One thing I need to point out here is that, and that's often a confusion, we're not assuming any constitutive law here, right? So we are just solving the force balance equation. So we're not assuming any sort of spring-like behavior. And I'm actually going to emphasize throughout the talk that we think that these junctions don't behave like springs at all. but they're more like microscopic muscles that can control length and tension independently. Right, so there's force balance, but that doesn't mean that there's a constitutive relation. All right, so let's actually go to data. So this is sort of what a zoomed in snapshot of the raw data looks like from a membrane marker where we see the cell outlines. Then one can segment this and run this tension inference code. So this is, it looks like a simulation, but this is data. And so the color codes here for the tension with red meaning higher tension and blue meaning relatively lower tension. And so if you watch this patch evolve over time, you see that a very peculiar pattern of alternating high and low tensions emerges that you see sort of all over this patch. And as I continue this movie, you'll see that the high tension junctions contract and undergo T1 processes. And because there's this very nice pattern, these T1 processes are initially very coordinated. But then over time, as the T1s happen, they destroy that order and the flow actually ceases. So this is from, I'm going to run it again because it's fun to watch, right? So initially there's no apparent order in the tensions. The cells are nicely sort of hexagonally packed. We'll get back to that. Then this order emerges, and as a consequence of that order, you have these very nice coherent T1s, and then they destroy that order, and the tissue flow stops. So that's the story of the talk in a nutshell, and now we're going to try to understand this quantitatively, build a model for this, and so on. All right. So the first thing we can do is we can quantify these things for all the T1s and do the sort of a statistical analysis where we overlay the time traces of the relative tension for all the T1s leading, so on the tension on the junction that contracts leading up to the T1, and then that's sort of the new junction that elongates. And we see there's this nonlinear increase in tension on junctions that will undergo T1 processes. And we can sort of turn this around and use it as a prediction. So we can ask, given a junction, we infer the tension on it from the angles. How long does it take until this junction will undergo a T1 process? And so if we plot these things against one another, we see that there's quite a nice correlation. So we can predict in the future by sort of 10 minutes or something, or I guess, yeah, it's about 10 minutes here, when a neighbor exchange will happen, just based on geometric information. So then let's ask, is this the only way that a T1 can happen? Well, what I showed you here came from the lateral part of the embryo, the actual germ band, where all the myosin is, so where this process happens actively. If we look on the dorsal pole up here, where there's very little myosin, the T1s are passive, and if we look at the tensions, they behave very differently. There's essentially tension homeostasis, so the relative tensions stay constant, which means that this behaves sort of like a passive foam, right? So the angles stay at 120 degrees. Then the neighbor exchange happens, and then of course, just by geometry, if the angles here are 120 degrees, then the new angles here have to be 60 degrees, which implies that now this inner junction is all of a sudden under very high tension from the neighbors, and so it will expand very rapidly. And that's exactly what we see here, right? So it sort of snaps apart. Okay, so we have a way, geometrically, again, this is just geometric information, to distinguish between active and passive T1s. We can also predict when active T1s will happen, just based on the tensions. Can we actually do even more with this? So to do even more, let's have a look again at the force balance condition. And let's think about it a little bit differently than before. So before, we had this mindset, we observe the angles and then we infer the tensions. But force balance can also be read the other way around. I can tell you, I give you some tensions, and then they act as a constraint on how the angles must be at each vertex, right? And so now we're going to switch a little bit into this constrained way of thinking. So if you have force balance, that means the tensions have to form a triangle, right? Because they sum to 0. They have to close the loop. We can rotate this triangle by 90 degrees. And then we have complementary angles in the triangle and at the vertex. And this we can do at every vertex. So because the vertices have junctions in between them, they have to share these edges in the triangulation. All these triangles have to form a triangulation. So that's sort of a geometric manifestation of force balance. is that the tensions triangulate. And so then, here's sort of where this constrained way of thinking comes in. We can ask, given the triangulation, which means we're given the tensions, can we reconstruct what the cell geometries must be? And so a very nice procedure to get a polygonal tiling from a triangulation is the Voronoi-Delaunay duality, which given a triangulation produces a tiling by making the circles for each triangle and connecting them along the connectivity of the triangulation. And so it turns out, and we just figured this out a few months ago, that this is actually the polygonal tiling that is in the absence of external forces, that the cells will take in the absence of external forces. So this is sort of the free boundary conditions case. I don't have time to explain this, and we're not 100% sort of clear on the microscopic derivation of this, but we have sort of arguments for this from sort of macroscopic scale and also coming from the microscopic scale. So I'm happy to talk about this more offline. But it also means that we somehow have to have a way to accommodate for external forces that we apply at the boundary of a tissue. And it turns out that these exist in the form of shear or dilational transformations of a polygonal tiling that preserves the angles at all the vertices, right? So you can do that. You can't do that in a triangulation, obviously, but you can do it in a polygonal tiling. And we call these isogonal modes because they preserve the angles at the vertices. And it turns out that these isogonal sort of microscopic angle preserving transformations are exactly the ones that correspond to externally applied forces or stresses. All right. So we can use this way of thinking to use the geometry from microscopy to distinguish in a tissue between actively and passively, so externally driven motion. So we can infer the tensions, so we can infer also how the tensions change over time. So that's going to be the active contribution. And from that, we can construct our sort of boundary force-free reference state. And then there are these isogonal strains, which we can infer geometrically. I'm going to tell you in a second how that works. And that are the external forces. And so then we can do that in a tissue. So again, this is sort of this flat map projection of the embryo. Over here is the head, here's the tail. This is the germ band in green. And this is this dorsal tissue in blue. And we see in the dorsal tissue, there's a lot of strain shown here as sort of these little green lines, extensional strain along the dorsal ventral axis. So this is a passive tissue deformation. There's external forces that act on that tissue that drive that deformation. If you look in the lateral ectoderm, in the germ band, you see way less strain, at least down here, than when it wraps over the pole. As it wraps over the pole, it gets sort of stretched. So that's that stuff over here. But we can infer the passive contribution to tissue deformation just based on geometry. All right, and so this is how it works. Basically what you do is you construct for each vertex, you infer the tensions, you construct the local tension triangle, and then you look for the deformation tensor, shown here sort of pictorially, that transform the tension triangle into the centroidal triangle. So if you connect the cell centroids, that also forms a triangulation. And the transformation from one to the other gives you this passive strain. So this is not at all obvious why it works like that. Again, I'm happy to talk about it offline. For now, you'll just have to trust me. So we found this really cool, and we can do even more with this, but I want to take the rest of my time to talk about how we can turn this into a predictive model. Okay, so unless maybe this might be a good time to actually pause for questions. Okay, great. Either I'm way too fast or everything is crystal clear. Okay, so here's the idea for a model. We write down some energy, elastic energy differential, which depends on dominant contributions. So we have some small parameter epsilon here. So to 0th order, we have the tensions. But again, these don't come from a constitutive relation, so they're just prescribed numbers for now. And we have pressure that counteracts. It's like a Lagrange multiplier that counteracts these tensions, right? So otherwise the whole thing would collapse, obviously. And then there's sort of subdominant contributions. So you can think of these as cell internal contributions to elasticity, like the cell nuclei that once they bump into each other are sort of squishy and they repel each other, or something like microtubules, or actomyosin structures that form in the bulk of the cell and not along the adherence junctions. But we're assuming, and that's really a central assumption here, that these happen on a force scale, on an energy scale that is much smaller than these dominant junctional forces. Okay, so then we can take this, we can minimize the energy, and essentially what I told you is that that's sort of this Voronoi procedure gives us a geometric way to minimize that energy, and then external forces act on that Voronoi, on these geometric constraints that are encoded in the Voronoi to give us the actual tissue geometry. And so as these tensions now change over time, adiabatically, the tissue deforms in quasi-static force balance, right? So that's really the idea, that the flow is not driven by forces that are imbalanced and act against friction or viscous dissipation. The tissue deforms in quasi-static force balance because these tensions that are balanced change over time. So the geometry, sort of these geometric constraints change. Okay, so before I get to how we change the tensions, I want to make an analogy that maybe helps understand this a little bit better. If you think about a foam, it's actually sort of the most simple example of this kind of thing that you can do, where all the tensions are identical because it's just sort of the surface tension of whatever fluid you're using to make your foam. So all the angles want to be 120 degrees, and a foam is a solid, right? It can hold some shape. Of course, it has a fairly low yield stress, right? It's very easy to deform, but nonetheless, for small stresses, it behaves like a solid. And that's really the key here. And now we are thinking of this basically like an active foam that can internally regulate the surface tensions on each junction individually. And it's not a 3D foam, it's a 2D foam, so that's what this little thing down here is for. Okay, so the model that we come up with is very simple. It's a local feedback where each tension locally tries to amplify itself. There's a lot of microscopic evidence for positive feedback like this. Myosin behaves like a catch bond, and there are other sort of feedback loops that can drive positive feedback acting on myosin motors. But there's a limited pool of myosin in each cell. And here we cheat a little bit. And we assume that the limited pool is not per cell, but per vertex, because that just makes the formulation simpler, because then we can formulate everything based on the triangulation. Because that is a constraint, so this we do in each triangle, basically. Okay, so let's see how that can give us T1s. So here we have a pair of triangles corresponding to this quartet of cells. We assume that everything is periodic, so we just tile periodically, and then we run this positive feedback. So what happens is you get the amplification of the tension in the middle. I'm going to run it again. So this edge initially is a little bit longer, so it's going to amplify itself on the cost of its neighbors, and that leads to this neighbor exchange. Because you have in the background, the black cells basically show you the Voronoi, and once you hit the Delaunay condition, I'm going to explain in more detail what that exactly means, which is just a condition that the Voronoi can't be self-intersecting. You have to do the neighbor exchange. Now what happens is that the tension on the new junction is very high. It's higher than the neighbors. And if you think about microscopically what happens there, with a myosin, we actually get little myosin on that new junction. So if you think about a junction that has high myosin, it contracts. Where does the myosin end up? Well, it's going to end up in the two cells that just have lost contact. And so then when you make a new junction, that new junction between the two other cells will have comparatively little myosin on it. But geometrically, we know that there has to be a lot of tension on this to be in force balance. So it can't be in force balance. And so transiently, it's thrown out of force balance. There's some sort of passive contribution here. Imagine sort of passive crosslinkers turning over, like viscosity on the junction level. And that sets the time scale on which this new junction now elongates until force balance is reestablished. So that's how a single T1 works. Now we can ask what happens when we do this in an entire tissue. And so there are two things that we have to do. One is we have to have some initial anisotropy. to set the orientation of tissue elongation that we want to get out of these T1s. And we get to decide whether we start with a very nicely ordered packing of cells, as we observe it in the Drosophila embryo, or with a disordered packing of cells. So let's see what happens. Okay, sorry. So where does this anisotropy come from? So the idea is that because this is an ellipsoidal surface, that is pressurized internally, you have hoop stresses that are twice as high as the axial stresses. So this is this hot dog effect. And that would give you just a very simple geometric reason to have this stress anisotropy initially. All right, so now we can watch it run. The little colors here show the coordination number of the cells. So you'll see that as the T1s happen, they generate little topological defects, as was already pointed out several times before. And these destroy the order in the packing, and that stalls the flow in the case where we started very ordered. When we are initially disordered, we get less convergent extension, we get less deformation, because the cells can't coordinate the T1s. And so we can quantify this and we can compare it to the experimental data. So this is the length and this is the width of this piece of tissue. Starting in an ordered initial condition, we get a fast phase of convergent extension. Then as it becomes disordered, it slows down. When we start disordered, it's slow from the start. And if we look at Drosophila, we have equally a fast phase of convergent extension and then it slows down. And we also see, as I showed you in the movie earlier, that the tissue becomes increasingly disordered as it flows. We can do this more systematically, so we can really sweep out sort of a phase diagram where we change the initial tension anisotropy magnitude, and we change how ordered or disordered this is by basically seeding the cell centroids with a hard disk packing with different packing fractions. And then we can sort of roughly estimate based on the hexagon fraction as a measure for how hexagonally packed the cells are. We can estimate where the Drosophila embryo would be. So that's the little red star there. All right. So that's the tissue scale simulations. Now, for the last few minutes, I want to come back to this pattern that I pointed out earlier, this alternating pattern of high and low tensions. And so this is really intricately related to this increasing disorder in the tissue and the coordination of the T1s that allows for this efficient convergent extension flow. So we're looking for an order parameter to quantify these sort of this local motif of this pattern. So what we came up with is, let's look at the tension triangle shapes. So there are two configurations that are sort of polar opposites that we can distinguish. There are these sort of tension cables, or you could also say force chains, where if you look at an individual vertex, you have two high tensions and one low. In a triangle, that means that the triangle is acute, right? Two long sides, one short. Or you have this pattern with these alternating high and low tensions, which we term tension bridges for the lack of a better name. And these correspond to obtuse triangles, where you have two short edges and one long. So now we can think about the shape space of triangles to find an order parameter. And the way we do this is we start with an equilateral reference triangle, and then we do a sort of a geometric SVD, singular value decomposition, which means we rotate that triangle, then we stretch it. So that will determine whether it ends up obtuse or acute, right? So if I wouldn't rotate this and stretch it like that, then it would make an acute triangle. If I rotate it by pi over 6 and I stretch it, it makes an obtuse triangle. And then we rotate into its spatial orientation. So we have some intrinsic shape that is quantified by the magnitude of anisotropy and that phase, that orientation that determines whether it's acute or obtuse. And we have the spatial orientation. So in this shape space, in this intrinsic shape space, there's a threshold indicated here, which is the Delaunay condition. And that's just when one of the angles in the triangle is 90 degrees. And to understand that, we go back to Delaunay-Voronoi duality, circumcircle construction. You can show geometrically that corresponds to opposite angles in a triangle, in a pair of triangles, summing to pi. So if you have two identical triangles for simplicity, that means they're both 90 degrees. If you have obtuse triangles, that's fairly easy to do with low anisotropy. But if you have very acute triangles, then you need a lot of anisotropy to get to that point. And that's why that threshold is at very high anisotropy for the acute triangles, but then at lower anisotropy for the obtuse ones. And that sort of explains, because the obtuse triangles correspond to this alternating pattern of high and low tensions, explains why the T1s are so efficient if we have this nice alternating pattern. So we can quantify this in the data. We can see that there is actually this shape phase is increasing over time. So we go from something that is fairly evenly distributed along this phase axis to something that is highly enhanced in the obtuse side of the space, and then later on it becomes disordered. And we can explain this just based on this winner takes all positive feedback, which when we plot it out in this triangle shape space, gives us a flow that sort of goes into the top right corner, and so it very efficiently drives the individual triangles towards this T1 threshold. I guess in the interest of time, I'm going to skip the rest here. I'm happy to answer questions about it, just a short teaser, so we can turn this picture with this triangle shape space and so on into a mean field theory based on that construction. And in that mean field theory, we can then actually predict quantitatively the amount of tissue flow that we get given an initial amount of order in the tissue and an initial anisotropy. So this is Nicolas's poster. And so with that, I'm at the end of my talk, and I want to just briefly summarize that the tissue remodels while it remains solid against external forces, right? So that's the foam picture. This autonomous active plastic flow, which is only based on this local feedback, there's no global information that goes in, except the initial condition, is self-limiting, right? So the flow, because it drives disorder in the tissue, it stops at a finite, after a finite amount of deformation. And we have this way geometrically distinguished between active and passive contributions to tissue deformation. Thank you.
Questions for Fridtjof, Vincenzo?
Hi, nice talk. I just wanted to ask you a clarification. In comparing to the continuum theory that we inferred, there are two features there that struck me as somewhat peculiar. The first one is that we couldn't get a very strong agreement by assuming the first equation to be a Stokes plus the myosin acting as a little bit as a stress. And arguably that could be due to the fact that this medium is not incompressible, as that simplification assumes. But I'm wondering whether your microscopic analysis has any insight to provide about that issue. And the second is that in order to close that system of equation, we had to invoke some other fields. We used Ekaterina as a proxy.
Yeah.
Your analysis doesn't take that information. And I'm just wondering, is that because that information is only useful in establishing the gradients, or is it somewhere buried there? Could you please elucidate this comparison to the best?
Yeah, I mean, most of these things basically go into how can we now turn this discrete sort of agent-based model back into a continuum model. And that's sort of what we're working on. I want to point out that when we coarse grain, so this is, I guess, this. There are more tensors that pop out on the macro scale than just the myosin stress tensor, right? So even without invoking something like Ekaterina, sort of additional biological fields, just coarse graining already gives us more fields that could have something to do with it. But I also think that another, completely unrelated to this, another reason might just be the biology of the Drosophila embryo, where there are a lot of other things going on at the same time as this tissue elongation, right? So you have the ventral furrow, which ingresses, you have the posterior midgut, which ingresses, there's the cephalic furrow near the head, there's cell division starting to happen in the head, and so on. So unfortunately, in Drosophila, all of these things happen at once, and it becomes very hard to disentangle them. So I'm not sure how much a global analysis sort of can really reconcile these things quantitatively without taking these processes into account.
All right, let's go to 4 questions here on the right, and then we go back to the left.
Okay, very nice talk. So I have two questions, but given how long this line is, I'll just ask one. So the tension triangulation you described is quite similar to the so-called Maxwell-Cremona duality or the force tiles, right?
It's the same, yes.
Yeah. So when you go to this triangulation and calculate the inverse in real space, you may get multiple, which correspond to what you call isogonal mode, right? I'm wondering how that explains the passive versus active.
Yeah. So this would be, so the compact version of this is here, right? So from the triangulation, you make the Voronoi, and we can more or less show that that corresponds to the state where you don't have external forces acting on it. So all the forces are just on the junctions. And then these isogonal modes correspond exactly to external forces. So that's where, so it's this extra degree of freedom that comes in from when you go from a triangulation to a polygonal tiling that accommodates external forces.
So from the Voronoi tessellation to the triangulation, it's unique, right? Because you have only one stress. But when you go back, there is no external force, or the external force refer to the boundary?
Yeah, so that would be, it could be boundary, or it could be cell internal, like nuclei, for instance, right? I would also refer to that as external from the perspective of the network of junctions, right? So any force that does not live on that network of junctions, I would call external here. And any of these forces, if they're sufficiently small, would be accommodated by these isogonal modes. If they dominate, then of course that whole geometric constraint with the angles doesn't hold anymore, because we're assuming force balance at the vertices is determined alone by the junctional tensions, right?
Okay, I see. Yeah. Thank you.
Yeah.
Please go ahead, Mattia.
Wonderful work, Fridtjof. What I'm trying to understand is you start from an initial condition where you have basically your reservoir of energy, which is the frustration of your epithelium. Then from that, can you predict the later stages with this, evolution equation and match it to experiments? And if that's the case, does that mean, as you said, that this is cell autonomous, and therefore if you now compute the myosin at the initial time and you just advect it with the flow, you just conserve it along trajectories? I don't know if you did this comparison.
So the advection is again something that relates to the macroscopic, sort of the hydrodynamic coarse graining of this theory, which we haven't fully done yet, especially things like co-rotation we haven't fully worked out. That's a little bit subtle. But we can, at least in the tissue scale model, right, we can predict, right, so we can predict sort of the what's happening in Drosophila only given the initial condition. Right, and I want to point out there's not really a reservoir of energy, right? So this is not a relaxational dynamics in that sense. It's dissipative because the myosin is sort of turning over the whole time to maintain. It's like muscles, right? So even if you're holding a weight, you're dissipating energy because the myosin on your muscles is turning over, right? So what limits the flow is not some limited amount of energy. It's basically that the things when they are purely autonomous on a local scale, they are always destroying the order. Because the junctions that have high myosin, they contract, they lose that myosin, so they lose that information essentially. So that's a very simple way of thinking about it.
But that's a strong prediction that from initial condition you can just predict the future for some amount of time.
I think it works in Drosophila. It won't work in more complex tissues where you have something like planar cell polarity and other sources of information that act like as a compass in each cell that can maintain information that is not sitting on the junctions, right?
Right, Jose.
I'm going to ask a question that's going to sound really trivial, but I actually think it's a lot deeper than that. But isn't all active contractile systems, aren't they all plastic in a way? And maybe we should be calling at least the subsection of contractile systems active plastic solids conference, because in a way, sure, it's still a solid due to external stresses, but when your myosins are contracting the system, there's no going back.
Well, I guess it depends on what happens when you kill the myosin after the deformation has happened. I could imagine situations where the myosin is really acting against some spring-like forces, and so it would snap back when you get rid of the myosin. But the way we think about it here, it would just freeze in its current state, because killing the myosin would mean you kill the turnover. So the myosin heads would just stay attached, and so everything would just sit in its configuration, right? The way that this thing can deform plastically and that length can change while maintaining constant tension is because there's turnover, right? Because there's not a fixed reference length. The reference length, if you want to think of a spring itself, the reference length changes. Thanks.
Unit.
So when you put in the assumptions for the feedback, right, of the tension, basically positive feedback with the tension, I was wondering whether actually you have some way of testing this by comparing to experimental data, in the sense of, does it make a prediction of, let's say, the dynamics of the short time dynamics of the actual T1, and then you can compare, kind of test the assumption?
Yeah, I didn't show this. I have, well, I'm not going to go to it. I can show you the backup slide. Basically, the curves that I showed you earlier, here, these curves, we can reproduce these curves. So if that's short time scale enough for you, then yes. On even shorter time scales, there are pretty strong pulsatile fluctuations. So what looks like a continuous sort of smooth curve here, if you look at individual junctions, is actually sort of, it does this. So there might be some microscopic ratcheting happening that allows that sort of plastic sliding of the junctions. So on that shorter time scale, we don't have, like, the data doesn't give us that.
Right, Silke?
Yes, very nice talk. So what really strikes me in your approach is that you've essentially sidestepped the whole idea of having a constitutive law between a shape, the tension in a system, and you go backwards, you go from the stress formulation. In your approach, is there for two things? Is there a role for any apical stresses? And the second one, in the data sets you have and in this disorder transition, does it tell you anything about shape, stress correlations, and what might want to build into a model?
Okay. Apical stress, I guess, would refer to something that not, so stresses that are not on the junctions,
exactly,
right? Like apical constriction.
Yeah.
This would be external forces in our model. So here. So this would go into this term. I guess if it's isotropic, it would actually sort of modify the stress.
So you move this all to external,
we move this to external, yeah. And that's what allows the sort of this very nice geometric construction. And that really relies on having that scale separation here, right? So we are assuming that pressure differentials between neighboring cells, right? So the pressure is outside here. So we are not allowing large pressure differentials between neighboring cells. They would also go into this term, so they would also need to be on the scale of epsilon. And so that's sort of a strong assumption that goes into this. And if we can't make that assumption, then these things don't work.
And my second question.
Okay, so I'm not quite sure that I understand where you're going with this, but what I can say is that sort of this idea that disordered shapes in the sense of a high shape index correspond to a fluid state versus a solid state. That is not the case here. So this is very different from the classical sort of area perimeter elasticity vertex model. All of these things are solids. So this is the right slide for this. They all like foams on the short time scale, and they fluidize by changing the tensions. And they do this in a very controlled way here with this feedback, right? And so that gives rise to this, what we call active plasticity. You can also make it random, and then it would fluidize the system in some sense. Yeah.
But if I understand your theory correctly, or you effectively get out couplings between elongation and actomyosis and stress polarization, they're not always one-to-one. They change, right?
Right. Yes. So cell elongation and the myosin polarization or the myosin stress anisotropy don't have to agree here. They can be orthogonal or at any other angle. Yeah.
And then finally, Christian.
I think we're out on time. So I had two questions, but I'll ask just one. Just a conceptual one, general. So when you're doing this quasi-statically, you're assuming that, you know, one of the fast dynamics is purely mechanical, and then the other one includes the activity.
Right. Yeah.
That is not my understanding of these systems is that if we would kill them, they would behave completely different, even at the mechanical level. So that's not such a sharp distinction, right?
Well, I think the problem with killing it is it might depend quite sensitively on how exactly you kill it. So I was trying to allude to this earlier, right? So if you think about fixing it, for instance, right, you change the structure of everything. So you can't really compare things at all anymore. If you think about it, so like dephosphorylating the myosin to get it off of the junctions, it's also not quite clear whether there's some myosin that's left, but it's not active anymore, so it's just having both heads attached, and so now it's acting like a passive crosslinker. That's what I would think happens, but maybe the biologists disagree, or maybe it depends on the type of myosin. Muscle myosin might behave differently from non-muscle myosin. There are also passive crosslinkers themselves. They also turn over. The key to me is really that there's always this turnover, right? So when the thing just sits there and you exert an external force that exceeds what myosin can do against it, it will slide. Because the individual attachment points are turning over. They are detaching, they're reattaching, and every time you detach, you slip a little bit, you reattach, you have plastically remodeled your configuration. But that's happening on a time scale of minutes, right? So that's when sort of these turnovers are happening. And on a very short time scale, I would think that these things behave sort of spring-like, but with a changing rest length. That's the idea.
All right. Thank you very much for the questions, all of you. We now need to move on. So let's thank Fridtjof again.